Hello, science enthusiasts and curious minds. Today, we're diving deep into a groundbreaking announcement from the labs of CERN that has sent shockwaves through the scientific community. This new discovery could potentially alter everything we know about particle physics. So, buckle up as we explore the details of this startling revelation from CERN. CERN is once again at the forefront of scientific discovery, captivating the world with an extraordinary announcement from its famed Large Hadron Collider. This breakthrough could redefine our comprehension of the universe. Scientists at CERN have stumbled upon anomalous readings that intriguingly hint at the possibility of extraterrestrial life in a parallel universe. In this video, we delve into CERN's groundbreaking revelation that could change everything. During a recent experiment with the Large Hadron Collider, CERN's physicists observed something unusual in the behavior of a particular type of quark. Quarks are the fundamental constituents of matter, coming in various types known as flavors, each with unique properties. Among these, the beauty quarks captured their attention due to its peculiar instability and rapid decay, surviving only about 1.5 trillionths of a second. What's truly baffling is the decay pattern of the beauty quark. According to the standard model of particle physics, when a beauty quark decays, it is influenced by the weak force and should transform into leptons lighter particles such as electrons or muons with an equal likelihood of becoming either. However, the data from the Large Hadron Collider paints a different picture, challenging established predictions and possibly pointing us toward new, uncharted territories in physics. This discovery at CERN that beauty quarks decay into muons only 70% as often as they decay into electrons has sparked significant intrigue. Remarkably, electrons and muons are nearly identical in all aspects except for their mass. A muon is 200 times heavier. According to the standard model, which dictates the interactions of subatomic particles, this weight difference shouldn't influence the decay rate into these particles since all forces should act equally upon them. Yet, the observed data contradicts this, suggesting that both particles should be produced by the beauty quark's decay equally often. This anomaly could only be explained by the presence of an entirely new type of particle, one that has yet to be observed. This leads some scientists to theorize the emergence of a new type of physics, perhaps a new force-carrying particle that could radically expand our current standard model, answering long-standing questions and opening new frontiers in particle physics. The standard model is the reigning framework that has, until now, precisely described the fundamental constituents of matter and their interactions. But this unexpected discovery points to its limitations and the tantalizing possibility that it's not the complete picture. Despite its precision, physicists recognize that the model is incomplete. This latest finding from CERN could be the key to unlocking the next level of understanding in the enigmatic world of particle physics. As scientists delve deeper into the mysteries of the universe, there remain significant gaps in our understanding, particularly within the standard model of particle physics. This model adeptly explains three of the fundamental forces: the electromagnetic force, the strong force, and the weak force. Yet, it falls short of accounting for gravity and fails to explain dark matter, which constitutes the majority of matter in the universe. During recent experiments, researchers at CERN observed anomalies in their data that did not align with predictions made by the standard model. Such deviations aren't typically rare given the massive volumes of data generated by the Large Hadron Collider, LHC. However, this particular set of anomalies has drawn keen interest from the scientific community, prompting a more thorough investigation into what could potentially be a groundbreaking discovery. The scientists are exploring the possibility of a new fundamental force, tentatively named the prime force. This new force, believed to be incredibly weak, hence its previous undetectability, could fundamentally change our understanding of particle interactions. The Z prime force is theorized to affect electrons and muons differently, which might explain the unusual decay patterns observed in beauty quarks. If confirmed, the discovery of a new force-carrying particle would be one of the most significant breakthroughs in physics in decades, potentially leading to new fields of study and a deeper comprehension of the universe's most elusive forces and particles. If this discovery is confirmed, it could crack open some of the universe's most enduring mysteries and provide answers to vexing questions like the nature of dark matter and the full implications of the Higgs boson's role in shaping our reality. Some theorists propose that this elusive new force might even bridge the gap in achieving one of physics' loftiest aspirations over the past century: the unification of the fundamental forces of nature. The Large Hadron Collider, LHC, renowned for accelerating and colliding beams of particles, like protons and heavy ions such as lead, dedicates 1 month each year to probing these interactions. The primary mission of the LHC is to test various predictions of particle physics theories, including searching for a vast family of new particles anticipated by these theories and analyzing the properties of the Higgs boson. Hadrons, subatomic particles made of quarks held together by the strong force, much like how electromagnetic forces bind atoms and molecules, are a primary focus. Among these, baryons such as protons and neutrons are well known, but the LHC also investigates less familiar hadrons like the pion and kaon mesons, first discovered during cosmic ray experiments in the mid-20th century. By bringing two opposing particle beams into collision, the LHC sets the stage for these particles to collide and scatter, creating a spectacular burst of new particles flying in all directions. Each collision offers a snapshot of the underlying forces and particles, potentially unveiling new physics that could redefine our understanding of the universe. These fleeting particles created in the LHC have ephemeral lifespans, existing for mere fractions of a second or even milliseconds before decaying into oblivion. By manipulating various types of particles, researchers can unearth new particles amid these brief bursts of existence, all while relying on cutting-edge, highly sensitive technology. Detectors encircle the collision sites, capturing every shred of data from the collisions to ensure no detail is missed. This immense volume of data accumulates rapidly, demanding extensive time and manpower to sift through. The LHC is a powerhouse of data production, generating over 15 petabytes of raw data annually from these collisions. Scientists meticulously analyze this data, sorting through it to pinpoint the information they need. A notable achievement came in 2017 when the LHC archived over 200 petabytes of data in its tape libraries. To put the scale of this data into perspective, 1 petabyte is equivalent to about 250,000 movies. The Higgs boson, a fundamental particle associated with the Higgs field, represents a unique phenomenon in particle physics. It is the quantum excitation of the Higgs field, akin to ripples across the surface of the sea. The boson itself stands out as a completely new type of entity in the zoo of particles. Unlike elementary matter particles or carriers of quantum interactions such as the electromagnetic, weak, or nuclear forces, the Higgs boson occupies a unique position, bridging gaps in our understanding of the universe's fundamental structure. The discovery of the Higgs boson at the Large Hadron Collider was a groundbreaking achievement made simultaneously by two major experiments, a TLAS and CMS. On July 4, 2012, CERN announced this historic find, marking a significant milestone in particle physics. The newly discovered scalar boson was initially observed in two rare decay channels that provided the clearest signals. One involved the decay into a pair of photons through a purely quantum virtual process, and the other was the direct decay into a pair of Z bosons, which are carriers of the neutral-weak interaction. Although the discovery of the Higgs boson seemed to complete the standard model, it was just the beginning of a deeper exploration into this elusive particle. Since 2012, one of the significant milestones has been the confirmation of the Higgs boson's decay patterns aligning with earlier predictions. However, the journey to fully understand the Higgs boson is far from over. With the third run of the LHC and the upcoming high-luminosity upgrade scheduled for completion in 2029, researchers are poised to delve even deeper. This upgrade will enable the LHC to conduct more collisions, dramatically increasing the chances of uncovering exotic physics phenomena beyond the standard model. CERN estimates that with each year of the accelerator's upgrade, it will produce 15 million Higgs bosons, 5 times the number generated in 2017. This surge in Higgs boson production could be crucial for detecting other flavors of the Higgs boson. Some theories that extend beyond the standard model suggest the existence of up to 5 different types of Higgs bosons, each potentially offering new insights into the fundamental workings of the universe. The elusive Higgs boson, while not as frequently produced as the primary Higgs boson, continues to intrigue scientists, especially with the strong evidence already gathered for a magnetic version of this particle. But why is the Higgs boson so crucial? The Higgs field, to which the Higgs boson is closely tied, played a decisive role in the universe's earliest moments. It shaped the very nature of the vacuum that permeates our space-time, determining the existence of matter and interactions as we know them. It is responsible for giving mass to all known elementary particles, making the formation of atomic elements, stars, and even life itself possible. Without the Higgs field, and by extension, the Higgs boson, none of these would exist in our universe. The Higgs boson is often called the God particle, a nickname popularized by the media after its discovery. This term originated with Nobel Prize-winning physicist Leon Lederman, who, out of frustration with the particle's elusive nature, referred to it as the goddamn particle. When Lederman wrote a book about the Higgs boson in the 1990s, he wanted to use this colorful term as the title, but his publishers insisted on changing it to the God particle. This shift in terminology has led to an enduring, albeit misleading, association between the particle and religion, an association that still irks many physicists today. Despite the controversy surrounding its nickname, the importance of the Higgs boson and the Higgs field cannot be overstated. They are fundamental to our understanding of why particles have mass, a cornerstone of the standard model of particle physics. This crucial aspect of the Higgs boson and its field means that without them, there would be no stars, no planets, and no people, a reality that gives some justification for its dramatic nickname, the God particle. But why do scientists continue to study the Higgs boson? Beyond the essential task of precisely characterizing this new particle, there are 2 main reasons for ongoing research. First, scientists aim to understand how the physical vacuum of our universe was created in the early moments after the Big Bang. This vacuum is not empty, but filled with the Higgs field, which plays a vital role in giving particles mass. Second, researchers want to explore how this physical vacuum can remain stable over time. The Higgs field is unique in that it provides a non-zero mean energy to the vacuum, which is crucial for the existence of the universe as we know it. Scientists believe there might be a way to access the shape of this energy potential, which is responsible for the electromagnetic force, with its infinite range, and the weak force, which acts at very short distances. To investigate this, they need to study how Higgs bosons interact with each other, requiring the production of Higgs boson pairs. While the Higgs boson has helped answer the critical question of how elementary particles gain mass, the mystery of its own mass remains unresolved. No symmetry within the current theory protects this mass, leading to potential instability. In fact, quantum processes could, in theory, destabilize the physical vacuum itself through quantum fluctuations. Fortunately, this hasn't happened, but it underscores why scientists continue to study the Higgs boson so intensely, seeking to understand the stability of our universe at the most fundamental level. The potential instability of the Higgs boson mass, while occurring on timescales far beyond the known lifetime of the universe, continues to drive scientists in their quest. They're searching for additional Higgs-like particles that could reveal the new physics necessary to stabilize the Higgs boson mass. This relentless pursuit fuels the need to analyze even more data and, if possible, access higher collider energies. This is why, even after a decade, thousands of scientists around the globe remain dedicated to this mission. But why did it take so long to discover the Higgs boson? Proposed in 1964 and finally confirmed in 2012, the lengthy timeline has puzzled many. The reason lies in the Higgs boson's challenging nature. It is both heavy and extremely unstable. Producing such a heavy particle required concentrating an immense amount of energy in a very small space, necessitating the construction of a high-energy collider. Once produced, Higgs particles decay rapidly in various ways, with only a small fraction of them standing out from the background noise. To identify these elusive particles, scientists built the largest and most complex detectors in history, analyzing hundreds of billions of proton-proton collisions to extract a clear Higgs boson signal. As for the more speculative question, could CERN have opened a dimensional portal? The mysteries surrounding CERN's projects and discoveries spark both excitement and concern. Will these endeavors lead us to groundbreaking discoveries, or could they inadvertently bring about our ultimate demise? The future remains as uncertain as it is thrilling. Conspiracy theorists have spun three major theories about what they believe CERN is really up to, and they range from the alarming to the bizarre. The first and perhaps most frightening theory suggests that CERN is attempting to open a portal to hell. Some people fear that CERN's experiments with subatomic particles traveling at near-light speeds could unleash forces that take us beyond the gates of the ultimate inferno. However, CERN has consistently clarified that its work with antimatter is aimed at better understanding matter and mass, not summoning apocalyptic doom. Antimatter, as defined by the encyclopedia, consists of subatomic particles with electrical charges opposite to those of regular matter. Supporters of the Big Bang Theory believe that antimatter was created during the universe's formation and should exist in equal amounts as matter. Yet, antimatter remains exceedingly rare. The second popular conspiracy theory tied to CERN involves the Mandela effect. This phenomenon occurs when large groups of people remember past events differently from how they actually happened. Some conspiracy theorists believe that CERN's particle experiments could be causing shifts in our reality, potentially pushing us into an alternate dimension and triggering widespread Mandela effects. The third and final theory takes a darker turn, with some conspiracy theorists claiming that human sacrifices are taking place at CERN. In 2016, a video surfaced online that purported to show ritualistic sacrifices occurring on CERN's grounds. The footage allegedly depicted several cloaked figures performing a ceremony that culminated in the stabbing of a young girl. However, according to The Guardian, CERN quickly responded to these claims, with a spokesperson dismissing the video as a hoax and emphasizing that such events have no place at the research facility. CERN quickly debunked the claim, stating that the supposed ritual was nothing more than an elaborate prank. Whether a police investigation followed remains unclear. It's no secret that CERN has long been a target for conspiracy theories, so it was no surprise when, on July 5, 2022, as scientists resumed operations after 3 years of upgrades and maintenance, new conspiracy theories began to surface online. While those hoping for sensational news might be disappointed, it's clear that CERN has no plans to open a portal to hell, the future, or any other dimension. Instead, beams of protons continue to race around the 27-kilometer loop of the world's largest particle accelerator, over 300 feet underground. For more than a decade, this powerful machine has been smashing particles together at incredibly high energies, helping humanity explore the uncharted frontiers of physics. In a remarkable achievement, the Forward Search Experiment FASER detector at the LHC recently accomplished something unexpected. It detected high-energy neutrinos created by a particle collider for the first time. With 153 events confirmed as neutrino interactions with a high degree of certainty, This milestone could significantly deepen scientists' understanding of highly energetic neutrino interactions in the universe. This discovery also holds the potential to unlock the secrets of how stars burn and explode into supernovas. Neutrinos, tiny subatomic particles found almost everywhere, are produced whenever atomic nuclei combine or undergo fission. This latest breakthrough at CERN represents a major step forward in our understanding of the universe's most fundamental processes. Neutrinos, often referred to as ghost particles, are among the most elusive entities in the universe. They are created in a variety of ways through cosmic rays, radioactive decay, particle accelerators, nuclear reactors, and even from the natural radioactivity of potassium in something as ordinary as a banana. Despite being massless and chargeless, these particles are nearly impossible to detect because they rarely interact with matter. In fact, about 100 billion neutrinos pass through every square centimeter of your body every second, yet you never feel a thing. Welcome to Blessovia Science TV, where we take you on an exhilarating journey through the cosmos and unravel the mysteries of science. We are excited to offer you the opportunity to become a valued member of our ever-growing community of cosmic enthusiasts and knowledge seekers. Exclusive access to cosmic content. As a member of Blessovia Science TV, you will gain exclusive access to a treasure trove of cosmic content, including documentaries, interviews with leading scientists, space missions updates, and awe-inspiring visualizations of the universe, live Q, and sessions with experts. Your membership will grant you the chance to participate in live Q and sessions with renowned scientists, astronomers, and space explorers. Get your burning questions answered by those who push the boundaries of human knowledge. Embark on a journey that spans the cosmos and join us in unraveling the secrets of the universe. Become a Blessovia Science TV member today, and together we will reach for the stars. Thanks for watching. Subscribe, like, and share. Don't forget to leave your comment.